there are questions, we may have office hours for the regular ones on Thursday at the same time as on Tuesday. But don't wait until Thursday because the homework is lengthy. All right. So what we need to do is we need to keep going with this power series expansions for second order differential equations. And goodness, I want not this slide, I want slide 43. All right, so I'm not quite sure where exactly we finished on the lecture last Friday, but let me start with one of the examples about what we call ordinary points. All right, so ordinary points. And I remind you, ordinary, if you have a general equation with coefficients P, capital Q, and capital R, ordinary points are the points where P of x is not equal to 0. Okay? So in this example, we're looking for a power series expansion for the solution of the Airy equation that looks like this around the point x0 equal to 1. And I remind you that you can actually find solutions around any point, and the series expansions may look completely different, okay, completely different from each other. So we're going to take a regular point, an ordinary point, and we're going to find the series expansion around x0 equal to 1. So what we're going to do is we're going to assume an expansion of this form. The idea here is that this is differentiable term by term, so we can write y prime equal to that if you differentiate with respect to n. Notice the constant term from here will disappear, so the summation starts from n equal to 1. And then one more derivative, the summation will start from n equal to 2. And then we will plug in all of these things in the equation. By the way, for the homework, I really want you to do all the calculations by hand. But if you want to work with Mathematica, for example, to match coefficients and do these things in symbolic calculations, you can do that for testing and checking your calculations. But I would really recommend that for this class, for this homework, you learn it the hard way. Otherwise, you're not going to learn very much. Okay? I did this to type the solutions yesterday, so I know the pain that goes with it. Okay? All right. So we're going to plug in all of these things in the equation that looks like y double prime minus xy equal to 0. So you notice this is y double prime. And then I have equal to x times y. Obviously, we're going to have to find some equation to allow us to compute the coefficients. So a little trick first that you may have to do this in your homework as well. You remember we work on an expansion around x equal to 1, and I see a lonely x there. So what you would need to do is you would need to transform that x to x minus 1 plus 1, right? Because the expansion, all the terms, all the powers around x minus 1 some power n. So we're going to write x as 1 plus x minus 1. If you do that, basically you will get two terms from the right-hand side. You can see you will get 1 times the series that you see here. And then x minus 1 will give you x minus 1 to the power n plus 1. So basically we have this equal to that plus that. All right? Now, if I can go back, you notice that there is a term here that the summation starts from n equal to 1. And this term starts from n equal to 0. So what maybe we need to do is we need to eliminate or separate the terms that have n equal to 0. So everything starts with n equal to 1. So if you do that, what actually you will get is you will get 2 times a2 plus this. So let's see how we get that. How do we get 2 times a2 from this? How are you going to get 2 times a2? From where is 2 times a2 coming? How about n equal to 0? The first term, what do you get? 2 times 1 times A2 times 1. That's our term. And then the summation will start from n equal to 1. And how do we get A0 there? Where do we get A0? Anybody? If you put A0 here, right, n equal to 0, you get A0 times 1. So that's it. So basically what we have is, we have this expansion that involves powers of x minus 1 to n. In all the summations, we start from n equal 1 to infinity. And then we have this lonely 2a2 and a0. So obviously 2a2 and a0 have to match together. They have to be the same. And then we can get an iterative equation for the coefficients an. So effectively, this is what we will get. The equation will look n plus 2 times n plus 1 times n plus 2 equal an plus an minus 1. And this will be applicable only for n greater or equal to 1. Okay? Now, usually when you get an equation like that, that's painful because this equation does not directly give you, let's say, A3 in terms of A2 and A4 in terms of A3. It involves an plus 2 and an minus 1. So this may be difficult sort of to write down explicitly what the coefficients will be, but certainly you can plug in this in a little computer program of one line, and it can give you all the coefficients that you need. So, and here's what we have done, right? So the first thing is 2a2 equal to a0. That's what I have here. So a2 equal a0 over 2. And then from this equation, what can we do? Can we compute a3? What do I need to put for n? If I put n equal to 1, this will be 3 times 2 times a3. If I put again n equal to 1, this will be a1, and this will be a0. So I can write a3 in terms of a0 and a1. And you can continue with a4, a5, but notice the coefficients a0 and a1 remain free parameters. Right? You're not going to be able to compute what a0 and a1 are, which means they are anything. They are free parameters. Okay? So if you put all of this together, back to your series, this is how your series will look like. For what I have done is I separated the terms that multiply a0, and I separated the terms that multiply a1. And remember, when you write the coefficients a2, a3, a4, most of the coefficients after a3, they involve a0 and a1, a0 and a1, a0 and a1. So we're going to have, let's say, x minus 1 cubed 6 times a0. But then you're going to have x minus 1 cubed over 6 times a1, right? You can see it from there. So effectively, we have two power series in the solution. And they multiply coefficients a0 and a1. And literally, what we have is, these are the two fundamental solutions of the second order equation. Can you see that? You remember the second order equation, right? This is a homogeneous equation, has two fundamental solutions, and we actually have gotten the two equations, the two fundamental solutions by doing this power expansion, okay? There is one with an arbitrary a0, and there's the other one with an arbitrary a1. I have no time to read and tell you every little detail. There's really nothing here, right? So I call one of the solutions y3 of x, the other one y4, and you see the familiar form that we have done for solving the homogeneous equation of second order differential equations. Okay. All right. So again, this was a simple problem, and the coefficients were really polynomials, okay? But we can expand these ideas to any sort of equation like that, all right? And discuss the situations where we have ordinary points, or points where p of x is not equal to 0. And I would like to define give you a formal definition of what an ordinary point means. So in general, if these functions, p of x and q of x and r of x, are not polynomials, can be sines, can be cosines, can be anything. So if they're not polynomials, a point x will be an ordinary point when these ratios of q over p and r over p are analytic functions at the point x0. And remind me, what's the definition of an analytic function? In simple terms. So when we say a function is analytic at a point, what does that mean? What do you need to remember for a function to be analytic? Something simpler. Through all of this. Because we're talking about power series expansions, right? So something being analytic means has a Taylor series expansion around that point, effectively. Okay? So in our case, this little p and this little q are analytic at the point x0. If I can write a Taylor series expansion, a power series expansion basically for them around that point x0. I mean, before when we work with polynomials, we said, assuming there were no common terms between p, q, and r, a point is an ordinary point if p of x0 is not equal to 0. Now I am extending this to any functions that they are not necessarily polynomials, right? So there's no such a thing as cancellation of terms between p and q. So in that case, these coefficients little p and little q have to be analytic functions. All right. So in that case, if they're analytic functions, you can guarantee that there is a solution about an ordinary point that also has a power series expansion around that point. So effectively, what we have done is we are trying to generalize what we have seen for this simple example before to the case of any functions, p of x, q of x, and r of x. So everything we did for the example, you can do it for this general equation. The only constraint, if these are not polynomials, is that the little p and the little q have to be analytic, so they need to have an expansion, a Taylor series expansion around x0. So in that case, you know you can actually compute this in this form. Can you actually appreciate the fact, right, that if little p has a power expansion around x0, and this has a power expansion around x0, can you see why y of x will have a form like that? Because if you plug in all of this, right, little p is a power expansion, little q is a power expansion, and y is a power expansion, you can compute the coefficients. Right? I mean, all terms then will be power series. Then you can match term by term and you can solve them. Okay? All right. So in that case, you can actually show when little p and little q are analytic functions that the general solution is basically this combination of the two fundamental solutions we have seen for second ordered differential equations. Y1 and Y2 will be independent, so the Roskian will be non-zero at x0. And of course, Y1 and Y2 are going to be also analytic, so they're going to have this power series form. So effectively, when you try to compute the solution, this solution, it will take the form of really two series that they give you two fundamental solutions that they're independent of each other. But the first task is to compute this, and then when you compute this, you will see that it gives you Y1 and Y2. All right, and of course, you may ask, and this is very important, it comes actually in all the examples, if you do this, and so little p and little q are analytic, and you compute the solution y, somebody will ask you, what is the radius of convergence of the solution y of x? Right, what is the radius of convergence? And there are two criteria in most problems, both of them are being discussed. So since p and q, they come with a power series expansion, so they have their own radius of convergence. The radius of convergence basically, can you see, what is the relation of the radius of convergence of p and q with the radius of convergence of this series y? What would be an obvious criterion? So when you write an expansion for P as in a power form, right, it has some radius of convergence around x0, some little interval. How do you think this radius of convergence for little p and q relates with the radius of convergence for y? What would be an obvious sort of thing to say? That the radius of convergence of p of y is equal to what? The smallest of the radius of convergence of little p and little q. That's the best you can say, right? It may be something different, but the smallest radius of convergence of P and Q will actually be the radius of convergence for the solution Y. Now, there is another way to compute the radius of convergence, and actually, this is very nice criterion. So remember that these functions, little p and little q, are really the ratios of capital Q over P and capital R over P, and we assume that P of x0 is not equal to 0, right? So that's when we divide. So if you look at P of x, for example, can be a polynomial, can be anything, possibly has some roots, right? There are some maybe x's such that P of x equal to 0. So this second criterion, it basically says that the radius of convergence of this solution is the distance between x0 and the roots of capital P. And again, this is a common sense criterion, right? You are expanding Q over P in a power series around x0. But the denominator is 0 at some points. Don't you think that the radius of convergence should be the distance between x0 and the roots of capital P? Does it make sense? Because at those roots, this Q over P blows up. All right? So again, the second criterion measures the distance between x0 and the roots of capital P. And the only thing I'm going to say, and I'm going to show you this with examples, you have to be careful because the roots of capital P may be complex. So when we talk about the radius of convergence, you have to take distance in the complex domain. Okay? So you have to be careful with that. So we will see some examples as we go around. All right. So let's look at the radius of convergence of different series. And again, because I'm going to be, before we solve the differential equation, right, we're going to be taking these ratios of Q over P. So let's say that we have a function that it's 1 over n plus x squared, and I ask you, what's the radius of convergence around x0 equal to 0? What do you think? So look at this expansion and tell me what is, don't look at the notes. I'm only looking myself at the notes to know where I'm going to jump next. So look at that expansion and tell me what's the radius of convergence. And you can use any of the, I mentioned to you 2 different ways, right, of computing this. I mean, one of them, for example, was the distance of x0 from the roots of the denominator. So what are the roots of this? When is this 0? When is the denominator 0? X equal plus minus I. So what is the distance of 0 from plus minus I? 1. So we know that the radius of convergence of this is equal to 1 with one of our criterion. The other criterion would be obviously the one that you also have to do in your homework, is the ratio test. So if you take the absolute value of the n plus 1 term divided by the n term, and take the limit as n goes to infinity, so this ratio comes to be x squared. So remember, the ratio test says that this has to be less than 1. So the absolute convergence takes place when absolute value of x less than 1. So again, the radius is equal to 1. So the ratio test and this distance from the roots of x0 give you the same answer here. All right, so let's do another example. So let's say that we have a function that is 1 over this. All right, and this polynomial has roots at 1 plus minus I. And let's take, I take x0 to be equal to 1. Can you tell me what is the, at least the minimum radius of convergence, right? Because really we cannot say more than that. But what is the minimum radius of convergence? What's the distance of 1 from 1 plus minus I? What is the distance of 1 from 1 plus minus I in the complex plane? If you take the point 1, and then you have 1 plus minus I. So what's that distance? All right? So for this point, the distance is rho equal to 1. Okay? Now, if the expansion is around the point 0, all right, the distance of 0 from 1 plus minus I is square root of 2. So in that case, the radius of convergence of the Taylor series expansion will be square root of 2. And again, it all depends around what point are you expanding. So if you're expanding around 0, the radius of convergence, at least the minimum, is square root of 2. If you're expanding around x0 equal to 1, the radius of convergence is equal to 1. All right. So this is actually the Legendre equation, and we will spend at least one lecture with this equation because it has very interesting type of solutions. The coefficients are polynomials. You can see 1 minus x squared, 2x, and this is constant, alpha times alpha plus 1. So the coefficients p is 1 minus x squared, q minus 2x, and r equal to this constant alpha plus 1. So one of the things you're interested in is to compute these solutions of the Legendre equations around x0 equal to 1. So is x0 equal to 1? I'm sorry, x0 equal to 0. And you can see x0 equal to 0 is an ordinary point because 1 minus x squared is not 0. If you put x equal to 0, this is equal to 1. So this is an ordinary point, which means the function little p and little q are analytic around x0 equal to 0. And what is little p is minus 2x divided by 1 minus x squared. And what is little q is alpha plus 1 divided by 1 minus x squared. So, and you notice if you look at the denominators of little p and little q, they become equal to 0 at x equal plus minus 1. So what's the radius of convergence when you expand around x0 equal to 0? So basically, when you are going to compute a solution in power series form, what is the minimum radius where that power series will be valid? Looking at the distance between this and that. What is the distance? Say it again. 1. All right. So the radius of convergence for this is equal to 1. And actually, when I mentioned here that the minimum radius of convergence is equal to 1, right? This is the best we can say. It doesn't mean that, that maybe the Legendre solutions don't converge for all x's, right? I mean, obviously, it's not going to happen because here, in general, because of this singularity, all right, x equal plus minus 1. But let me just tell you something interesting because I noticed there. So when you solve this equation, and we will do this in a forthcoming lecture, you will get two solutions. And one of those solutions terminates at a finite number of terms. So it converges for all x's. So you get two fundamental solutions. One converges for all x's. The other one obviously will converge for x between -1 and 1. Okay? So again, it's good to keep saying the minimum radius of convergence, right? This is what the criteria are actually giving. Okay, so how about this equation? What is the radius of convergence for this equation? And I'm using these equations because these are key equations, as we will see, hopefully even today. So what's the minimum radius of convergence for this? Around, for an expansion around x0 equal to 0. Obviously, x0 equal to 0, it's an ordinary point. This doesn't blow up. So what's the minimum radius of convergence? Yep. Remember, find the roots of the little p and q in the denominator and see when they get 0, and find the distance of the x0 from those roots. So what is that distance? We already have seen this example. What's the distance of x0 equal to 0 from the roots of this? So 1, all right? So the radius of convergence of this equation is at least equal to 1. Actually, let me state something that is a little bit more theoretical, but I think it is worth basically mentioning it. So let's say that we have the second order equation, and we plug in some initial conditions, because we need 2 of them. So let's say y at 0 is given, and I miss a y prime there. So y prime equal to this is given. Since 1 plus x squared is not 0 for all x's, right? And I'm looking again for solutions for real x's. So 1 plus x squared is not 0 for any x. Then from the theorem on the initial value problems that we talked about a few weeks ago, the theorem there guarantees that there is a unique solution for all x's. So basically, what we have done in earlier lectures, they say, if you have this equation and you have these initial conditions, okay, because this is not equal to 0 for any x, then there is a solution for all possible x's. But now what I am telling you with this power series expansion, we say there is a solution that looks like this for x between -1 and 1. Can you see the contradiction here? So what do you think happens? How the 2 theorems actually come together so they don't really contradict each other? So one tells you there is a solution for all x's. The only one tells you there is a power series expansion for x between -1 and 1, because that's the radius of convergence. It doesn't, something is wrong there. So how do we actually bring the 2 things together so nothing looks wrong? Well, the answer is very simple. This previous theorem that says that because this is not 0, there is a unique solution, it doesn't tell you that that unique solution admits a power series expansion. All right? So it has a nice, unique solution, whatever it is, but that solution may not have a power series expansion. Okay? So remember, what we are talking today is finding a solution that admits a power series expansion. I mean, we don't say find a solution of any form, right? We say find a solution that has a power series expansion. This tells you find a solution, and there is a unique solution for all x's. Here, there is a power series expansion for x, absolute value of x less than 1. So really, there's no contradiction between the 2. OK, so let me just, there is nothing here. So let me just move now to this concept of regular singular points. So we discuss the ordinary points. As you will find out, hopefully, in your graduate courses and in your research, most of the activities happens near singular points, right? You want to know what is the solution going to blow up, right? If it's a dynamical system, or it's a boundary layer in fluid mechanics, right? You want to know where is the solution going to blow up, and those points are singular points. All right, so it would be points where that capital P is equal to 0, but we are going to try to discuss the concept of singular points, but they're not too singular, right? I mean, it sounds stupid, so they're singular, but they are angular singular points. Okay, so we will see what that means. So for the ordinary points, right, I remind you, the idea was that little p and little q, they have a power series expansion around x0. They're analytic functions. So now we are going to look at points where p of x equal to 0. All right? So basically, particularly, you know, we are going to be doing expansion around a point where p of x0 is equal to 0. All right? So that seems to be a problem. So let me take the Euler equation. And by the way, you're going to have to use this in the homework as well. It comes out as one of the steps in solving many of the Bessel equations that you will see in the homework set. So let's take this equation and call the whole thing as L of y, given by x squared y double prime plus alpha xy prime plus beta y. And we are immediately going to identify that x equal to 0 is a singular point, but I am going to call it a regular singular point. All right, so let's see what a regular singular point is going to be. Actually, I am not even sure if this comes on this slide, so let me just check. Otherwise, I'm going to tell you with words, and I'm going to proceed. So this comes a little bit later, a little bit past the Euler equation. Can somebody look at the equation and tell me, okay, this is a singular point, but why should we call it a regular singular point? For example, if you take the ratio of the coefficient q by the coefficient p, what type of function of x you have? When you divide this by that, what do you get? In terms of x, what do you get when you divide the two things? 1 over x, all right. So 1 over x obviously is singular around x equal to 0, all right? But you know what? It's a mild singularity because easily it could have been 1 over x to 100 or 1 over x to square. So it's singular, but not too singular. And what I mean here, not too singular, implies that when I multiply by x, the limit of x times 1 over x as x goes to 0 is equal to 1. It doesn't blow up. So the singularity is not too significant. All right, so it basically diverges around x equal to 0, but 1 over x. That is not as bad. So we will see later on that when we divide this by that, if the product of that ratio times x converges, all right, then that point x equal to 0, it's a regular singular point. Okay? And similarly, by the way, if you divide this coefficient by that coefficient, what do you get? What do you get? What's the ratio of the third coefficient with the first coefficient? It's 1 over x squared. Now, for that coefficient, we will call that singularity to be regular when x squared times 1 over x squared, it's finite as x goes towards 0. Okay? The idea here is that these are singular points, but we will have some mild way to define what a singular point is. There can be much worse singularities than what we have seen. And if it happens that these points are regular singular points, you can actually get a power series expansion with no difficulty that will converge up to some minimum radius of convergence everywhere except x equal to 0 in this case. all right? Now, I told you this ahead of time because none of this really comes explicitly in the Euler equation because the Euler equation is very simple. So let me just tell you what the solutions to the Euler equation are and how you're going to get them with no power expansion. You don't need to go to power expansion yet, okay? So the Euler equation will admit two solutions that they're independent, right? Second order differential equation, and we're going to compute them. If you look at positive x's, the interval of convergence will be from 0 to infinity. So everything except x equal to 0 is the series will, the solutions will converge. And the solutions, we have a very simple form, will be x to some power r, where r is to be computed. So no Taylor series expansion, none of the above yet for the Euler equation. So the Euler equation admits solutions of the form x to the power r, where r is to be computed. And this is going to lead, obviously, to two different r's. And for each of these r's, we're going to get solutions y1 and y2. So I want you to look carefully at this Euler equation, because doing more complicated equations, like a Bessel equation, will involve the Euler equation in one of the steps. Okay? So the Euler equation admits solutions x to the power r, and these solutions are valid solutions from 0 to infinity, not including the point 0. So how do we compute these solutions x to the r and why actually this thing works? It's very simple. We're going to take the first and second derivative, plug it in, and see if actually we can compute what r is. So that's what I have there. Y equal x to the r. Take one derivative, take a second derivative, plug in, and basically you will get the equation L of xr. By the way, there is a reason that I am using all of this together in this nice notation. L is like the operator, x squared times second derivative plus ax times first derivative plus beta. Okay, so that is the operator L, but effectively when you plug in everything, you can immediately see you get a quadratic polynomial in R, all right, that has two solutions. All right, so for this to be equal to 0, this quadratic polynomial has to be equal to 0. And if you solve this, these are the two solutions. Nice. And these solutions can be, now all the complexity comes there. They can be real numbers and different from each other. They can be equal to each other when this argument in the square root is equal to 0, or also they can be complex numbers. All right, but not big deal because x to the power r, easy to handle, all right? So we define f of r to be this quadratic polynomial, all right, with the two roots r1 and r2, okay? And the idea is to discuss now what happens to the different cases. So if you take two roots that they are not the same, okay, you can show that x to the power r1 and x to r2, there are two independent solutions. If you compute the determinant here in w, you come up that the determinant is not equal to 0. There's really nothing fancy. So we have two linear independent solutions, and the general solution is some constant x to the power r1 and another constant x to the power r2. This is like similar to when we were trying solutions of the form e to the lambda x, right? Here we try x to the power r, okay? X to the power r. So again, if r1 and r2 are real numbers and they are not the same, the solution looks simple as that. And actually here is an example, with particular coefficients. If you try x to the r and you solve the quadratic polynomial, one of the r's is 1/2, another r is -1, and here is the solution. And actually you can immediately appreciate that this solution here blows up at x equal to 0, but actually for any other x positive, this solution works. Actually for x negative, it also works, okay? And if you want to see a plot of this solution for the Euler equation, it looks like that. Now, what happens when the two roots are the same? You remember we have seen this before, right? Where did we see things where two roots are the same that gave us headaches? How about when we were trying solution c to the lambda x, right? What happened when the two roots were the same? One of the solutions were e to the lambda x. What was the other one? Some function of x times c to the lambda x, right? So for example, maybe x c to the lambda x if it works, okay? So how about here? If one solution is x to the power r1 and r1 equal to r2, what do you think the other solution will be for the Euler equation? The answer is going to be x to the power r1, exactly like this, times log of x. Okay? And this it's extremely important, right? Because x to the power r1 defines basically the singularity of the solution of the first solution around x equal to 0. And then for the second solution, you get basically the behavior of log of x as well. All right? And you remember log of x goes asymptotically to infinity at x equal to 0, right? Remember the plot of log of x? So this is extremely important. For example, in fluid mechanics, right, you will see these solutions coming in all the time, x to r1 times log of x. And let me give you a trivial proof, all right, without any algebra. You remember we have defined L of xr to be our operator in the solution, and we wrote this as the characteristic polynomial times x to the r. You remember? So if the two roots are the same, I can write this as x to the r times r minus r1 squared. Can I do that? Because the two roots are the same. Yep. So let's do the following thing. So this equation then is correct if I have two roots that they're the same. I am going to take derivatives of the left-hand side and the right-hand side with respect to r. Why not? I'm going to take derivatives with respect to r. So if I put the derivative inside the operator, which is basically inside the differential equation, what is the derivative with respect to r of x to the power r? Now I'm testing your calculus. The derivative of x to the r with respect to r. What's the derivative of x to the r with respect to r, not with respect to x? It is x to the power r log of x. All right? If you have difficulties and you don't remember this, call x to the r y, take logs, then log of y will be r log of x. So this x to the r is e to the r times log of x on the exponent. So when you take derivatives with respect to r, you will get back x to the r times the derivative of the exponent with respect to r, which will give you a log of x. So if you do this and on the left and the right-hand side, on the right-hand side, the two terms will cancel at r equal to r1. And then you have L of x to the r log of x equal to 0. So x to the r log of x is another solution. No proof is needed. Proof is basically, no other complicated proof is needed. This is the correct solution. So in the case of equal roots, these are the two solutions of the Euler equation, and you can actually show, I mean, you can immediately see, by the way, just having the log of x makes the two solutions independent, but if you calculate the Roskian, you will see that the two solutions are indeed independent. And the general solution will be, again, x to the r1 times x to the r1 times log of x. So again, this is the solutions of the Euler equation if you have two roots of the characteristic polynomial that they're the same. So now we need to discuss what happens if the two roots come to be complex numbers. So this is an example, right? So nothing special. If the Euler equation looks like this, the two roots come to be -2, and basically the solution looks like this. And again, extremely important of having this log, because it sort of defines what type of singularity you have around x equal to 0, all right? You know, back in the days, you know, when I was a graduate student, everything in research, you know, in applied mathematics was being able to calculate asymptotic behavior of solutions in fluids and dynamical systems. And of course, a little bit more complicated than what you see here, but being able to identify the singularities, if they're 1 over x or 1 over x squared. And you know, you can see, you remember I was talking about regular singularities? Here, the singularity is 1 over x squared. It's really not a regular singularity for the solution, okay? And it's log of x divided by x squared. And you can see why the solution is singular, right? So because of the log, at x going to minus infinity, I mean, at x going to 0, the solution goes to minus infinity, and then rapidly grows up, has a maximum, and then asymptotically dies, okay? And if you ask if you have a problem where the system behaves like this, guess what? You don't really care that it goes to 0 at x goes to infinity. You really care what's going on there, because that's where all the physics is, okay? You really care at x equal to 0. All right, so the complex case fast. So we are going to have 2 roots, lambda plus I mu and lambda minus I mu. And so let me do all the tricks of calculus. The solution is x to the power r. And I am going to write x to the power r as e to the r log of x. This is what I described before, okay? So x to the power r is e to the r log of x. I substitute r being lambda plus, let's say, I mu, or lambda minus I mu, times log of x. I split the real part and the imaginary part, and the solution has this form. So can you give me the 2 independent solutions for this case of complex lambdas? I mean, complex roots. What are the 2 independent solutions for the Euler equation? X to the lambda, where lambda is the real part, times the cosine of mu times log of x, and x to the lambda times the sine of mu lambda of x. So suddenly, this famous Euler equation that comes everywhere in physics, right, admits these solutions that look very weird. And as you realize from your homework, if all the solutions were looking like that, you'll be very happy, because many of the solutions you will need to compute will be way more complicated than this. This is just the Euler equation that is the reference for many of these problems. So it's the easiest possible, okay? So again, the 2 solutions, if you want to write them explicitly, will be x to the lambda cosine of mu lambda of x, and x to the lambda sine of mu lambda of x. So let me just fast say that don't want to do an example. It's basically the same calculations, right? So, and you can see the behavior around x equal to 0. You're going to actually to be able to zoom to see how things are varying around for small x's. For larger x's, the solution looks like this. For small x's, it looks like that, okay? So, so this slide basically summarizes the 3 solutions. They are valid for x greater than 0. But actually, if you plug in, instead of x, the absolute value of x, you can get the same solutions for x negative. All right, so remember, in case you need it, the same solutions are applied for x negative as well. And if you want, for any reason, to compute the, so this is the absolute value, I mentioned it, when x is negative. If you want, for any reason, to do a solution, a power series expansion of the Euler equation around not the x equals 0 point, but around anything else. So if you want, for example, to compute the solution to this equation, can you tell me actually the general form, let's say, of this equation? How would it look like if x0 is not 0? If we repeat everything we discussed today, how does the solution will look like? So instead of having a solution that is of the form x to the power r, what do you think the solution to this equation is going to look like? X minus x0 to the power r. So everything we discussed will actually be true for this equation as well, right? By just changing variables. All right, so we discussed about the Euler equation, right? That has this very nice solution. And now we need to start extending things beyond the Euler equation and see how can we get the solution near singular points. And just in summary of what to be expected, if you have singular points in general, not for the Euler equation, you may get two linearly independent solutions that are bounded as x goes to x0. You may get only one of the two spatial solutions to be bounded, or maybe none of the two spatial solutions to the homogeneous problem are bounded, okay? So lots of different things can happen. And I want you to really remember that in applications, what you're interested is not what happens when x goes to infinity, right? You are interested, what is the order of the singularity, right? You are interested, okay, the solution blows up as x goes to x0, but does it blow up like this? Does it blow up like that? Does it blow up like this times log of x? This is what's of interest, because the type of singularity defines the behavior of the solutions around x equal to x0. All right, so let me, it's 11:22, and the light will go off. So we're going to try to solve second-order equations for singularities that are weak. And I already defined the singularities if Q and P are, the capital Q and P and R and P are polynomials. The singularities are regular when the limit of this is finite and the limit of that is finite. Okay? So if you take the ratio Q over P and you multiply x minus x0, and this limit exists, and this limit with x minus x0 squared exists, then we call that singularity a regular singularity. In general, if Q and P and R are not polynomials, we will extend this and introduce the following definition. We would like to call something a regular singular point when x minus x0 times this and x minus x0 squared times that are analytic functions at x equal x0. So basically, they have a power series expansion. So it's going to come up that for this case, when this is valid, when these two terms here are analytic at x equal to x0, we can actually find a power series expansion. And the power series expansion, I am going to give you the hint now, and you will read the notes, will be x to the power r, like the Euler equation, times some expansion around x0. So the Euler equation is going to be the first term, if you like, or the first multiplier in the solutions to this general problem. So you need to know the Euler equation. Once you know it, then you can compute a series expansion for y around x equal to x0. I am going to try, I cannot promise because I have a very busy schedule, to post the slides, the video by Thursday, so we can move forward. So please do watch the website for any downloads. Okay, so I'll see you on Thursday. Thursday, yeah, office hours on Thursday.